I hope that this will lead to collaboration between you and Ramandeep and myself as well in the future. So thank you again, and over to you.
Thank you. I'm looking forward for the collaboration, and thank you for inviting me for this talk. So I'll just give a brief overview of what we have been doing with a collaborative team of UAVs and ground vehicles for coverage and monitoring applications in this talk. So if there are any questions or anything like that, you can just send me an email later on if you want to, even for the students if they want to collaborate. Okay.
Wonderful. Thank you.
Okay, so overall goal is that basically like we want to do a large scale monitoring. Let's say you want to consider wildlife habitats, let's say national parks, right? Or marine geological systems, monitoring mangroves, right? Or any other even desert wildlife habitat, like monitoring wild ass, or monitoring the vegetation of these kind of a large scale areas that are of interest. So there are two ways of doing it. One, you can use the traditional satellite systems. Of course, they are getting more and more highly better resolution, but at the same time they won't be able to give a higher resolution at which you can extract an a different set of information that is available. So this is where the unmanned aerial vehicles, or the UAVs, play a key role in obtaining visual information from which you can do a much more data analytics or visual analytics on the kind of habitats that are there. And of course, doing any kind of a manual wildlife habitat monitoring is always a very tedious, time consuming task. And let's say that you want to do an animal consensus. Let's say you take an wild ass project, right? So you want to know how many wild ass are there in in the run of Kutch, because that is the only place where they're living as of now. So traditionally what they do is basically they take an Cessna aircraft from the nearest airport. They go to the sanctuary and then see from the top through their windows, like how many wild ass that they can see, and then they make a note of it. Okay, so this is how it is done. So sometimes they will do for 1 hour or 2 hours, and sometimes it may not be able to finish. They may go the next day, but these wildlife can move from one day to another day. Then you'll have a double count. So the and doing in manually has its own issues. Although given the situation, so that was the only way in which they could do at the time. Right. And doing an urban area mapping, this was a project that we did with Professor Arora. Already did for Chandigarh, but so urban flooding is one of an rising phenomena because of the change in global change, global climate change. And then you also have purging of all the water bodies in cities. So what happens is basically like when there is a sudden rains, then the water doesn't know where to go, and then you just start to have flooding everywhere. And this causes both, you have a large scale economic loss as well as human lives, right? And also the other one was, as I said, with Professor Rada, that we did for the land records. So UAVs have a nice niche or in these particular applications. One, it's pretty easy to use. You don't need a highly trained pilot, but you need a little bit of training. And mapping softwares are already available so that you can just directly start to use it. It is always nice to know what goes into the mapping software, but at the same time, even black box also helps out. So only one of the main issues with any of these UAVs is that it has limited flight time. Let's say that you take a DJI Phantom 4, then it has a 20 minutes flight time. So you have two questions that you want to address is, before the end of the flight time, do you want the vehicle to come back to where you are? Or you will go to some other location and then ask the vehicle to come to that location, right? So basically like you're doing some kind of an optimization, either you by selecting the current location or you are going to some other location to find the least amount of parts. So these are some of the questions that we will try to address in this talk. So some wildlife, photography or mapping time that we did in Run of Kutch. Here you can see at 50-meter altitude, you have some 9 or 11 wild ass. So this is interesting because the same wild as when we tried to do it early in the morning, they were running away in all directions. But when we did at in a peak afternoon around 2:30 or so, so they were just stationary over there. Maybe they're too tired. So, but anyhow, so we were able to get some nice pictures from which now you can think that. So one of the first questions is we don't know how they look at different altitudes, right? So we were first trying to get some pictures of these wilders so that we know at what altitude these are, the camera footprint versus the size of pixel sizes of these wilders can be properly matched, so that you can start using vision and algorithms, either using deep learning or the traditional algorithms that will work out in these cases. So these were done at 50 meters. We also did it at 120 meters, but hardly there were like 5 or 6 pixels in that case. So then at 120 meters it seems almost impossible. So 50 meters was something that we thought is a good idea, but we could not further go back and then redo that thing. But what gave us the motivation was, especially when we were in the field, is you have such a huge, I think it was around 5,000 square kilometers or something like that. So if I want to do using UAVs, so how do I do it? So now where should I keep my base stations? How many refueling stations do I need? So this leads to one a very interesting problem. So wherein, let's say you want to do any kind of a national park that you are interested. So as of currently, what you do is you just go to this location, right, the square, and you go around and then do for, like, say you're taking your P4, then you're doing for that until all the locations, until all the area within your current location is fully covered, you keep doing it, right? You fly, you bring it back, change the battery, you fly, bring it back. Okay, so we want to do a better path planning for area coverage, and we want to use, it's not just that we want to be always stationary. Let's say that I start my mission over here and then I go to some other location, and then the UAV can basically like try to fly around and then come back doing some part of the mission. So now the questions that we want to ask is that, okay, what should be the path of the UAV? What should be the path of the AUV, sorry, under refueling vehicle, RV or UGV, so that you can, with minimal number of refueling locations, you will be able to cover the complete area. So we are only looking at area coverage. So that means you just need to cover the entire area only once. Okay. So the objective and the constraints. So you want to minimize the total UAV fuel consumption. Okay. We want to use the mission vehicle or the vehicle that is being used for deployment as the refueling vehicle, right? So that means that it is typically now properly manual vehicle, so that it has sufficient amount of fuel required, or you can make it as an unmanned aerial vehicle which has sufficient number of sufficient fuel, so you don't need to worry about fuel of the vehicle. So but the UAV needs to rendezvous on the AUV, so that you on the UGV, so that you have a automatic refueling system which takes the battery out and then puts in a new battery. So we assume that that kind of mechanism exists. So you have a constraint that the rendezvous with the UJV at a pre-decided locations for refueling. So where should these locations be? That is a part of the optimization problem that we will try to solve. So other assumption is basically that UAV speed is always going to be greater than the UGV speed. However, at the time of landing, we assume that UAV speed is 0. So there is some variability, but when it is moving at a constant speed. So UAV has a finite fuel, and then UGV has unlimited fuel and restricted to move along some paths only. So we assume that because it's, let's say you take any kind of a national park, you have the ground vehicle needs to move only in the roads, right? So that means that its paths are, the motion of the ground vehicle is fixed because of the roads. Okay, so that limitation also we take into account. And then we say that 2 consecutive refueling stations for the UAV must be within UGV distance of each other, which basically means that I should not have a location of the UGV saying that you come and meet me after like say at 100 kilometers or something like that, where the UGV can go because it has the fuel capacity, but the UAV is not able to go, right? So this means that whatever the distance that the UAV can cover within its fuel time, your the other UGV distance should not be greater than that. Okay, so how do we, so this is the problem statement that we got. So okay, fine, so how do we solve it? So we are interested in coverage, right? So which basically means that we can take pictures at certain intervals, right? So that these pictures are not too much overlapping, so that you don't get too many number of pictures, too many data points that are required. But at the same time, because you're taking the footprint of the camera, you can grid it up. So we can say here we have the red color dots. These are the points where the UAV should go and take pictures. Okay. And the yellow color path is the path, is the road network for the UGV, which it needs to be on this road network only. Okay. So for this purpose, so we place the grid points in the area based on the field of view of the camera. And then UAV must visit each of these points only once, because this is a coverage. So once you go to this point and take a picture, you will get the information around the picture, right? So if you take multiple times going to the same point, you don't get any additional information. But going to the same point will result in you losing a lot of fuel, because you're just going to the same point again and again, which is of no use, right? So for the UGV, what we do is we discretize the entire path into small chunks, let's say, which is given by this delta with some parameter alpha. We say that, okay, I don't want uh, two refueling stations to be within 1 meter. So it has to be, let's say, a maximum distance needs to be within 10 meters only, something like that. So then for every 10 meters, then I can have one refueling station. But what I will do is that through my optimization problem that I'm setting up, I will pick those stations, refueling stations, that are going to be used only. The rest of them are basically like just for possibilities that this could be a stations for the optimization solver to solve the problem. Okay. So now we have a setup which basically tells that given a set of targets T, which is nothing but my points on the area where I need to take pictures, okay, and a set of refilling sites, which is basically these are the points that we use the delta information, these blue dots, okay. Given these two, you want to plan tours for the UAV and the refueling vehicle, or UGV that we call, such that the UAV visits each target only once, okay. So when we do the problem constraint, then basically like when get into the technicalities, then we do need a little bit of degree and subtour elimination constraints that I'll get back to you. Okay, and then you have UAV and RV rendezvous at the refueling sites in S2 refuel. Let's assume that you have a refueling station from current location to a location that is 10 meters. If the UAV goes to that location and the UGV is not there, then the UAV will wait, okay, until the UGV comes, and then it lands on the UGV. If the UGV or the RV goes there first, then it will wait until the UAV comes there and lands on it. Okay, so that is an assumption that we consider. So UAV never runs out of fuel. So okay, sorry, this should be UGV. UGV never runs out of fuel, and minimize the total fuel consumed by the UAV. Okay, so to minimize the total fuel consumed, which basically results in total mission times. So the number of times that you need to deploy the vehicle is reduced. So if you reduce the number of times that you need to deploy vehicle, then the time that you take to complete the mission is reduced. So indirectly, all these have links. Okay. So what we do is that we formulate this as an mixed integer linear programming. Okay, why? Because in if I don't take mixed, right? So integer linear programming will only tell you which points that I need to take. Okay, but you have the UAV fuel, which is a continuous variable. It is not a 0 or a 1 variable or an integer variable. Okay, so similarly, the UGV is also a continuous variable. It is not a integer variable. And hence you have the MILP, which is basically like you have the linear programming for formulation that you did is having both the integers as well as the floats, or you can say the continuous variables. And hence you have the problem to be an mixed integer linear programming problem. Okay. So a little bit of math, but not too much. So our objective is this F. Okay, let me see if I can use a pen. Yeah. So our objective is F. And then you want to minimize your fuel. Okay. So what is happening here is that, so you have these red color dots, which are your target points, right? That we have, right? And then we have this blue color points, which is basically my the UGV locations, right? So what I'm doing is that, so you want to minimize Fij. So I'm going to make this thing into a graph, right? So from each point, so it becomes an all node, all graph, all connected graph it becomes. So when it becomes a graph, then you have an edge ij. That means that, let's say I take this as my I, and then j, then I have a graph. Okay. So what I'm doing is that I'm taking all the target points and then all the UGV points, and then I'm creating a big graph. Okay. So hence I have the variable corresponding to this particular edge, whether this is selector or not, is given in ij. Okay. So ij is going to be either 0 or a 1. So you have the integer part also coming into there. Okay, so Fij is a continuous. So Fij is only the cost that tells you, if I select this particular edge, what is the cost associated to it. So now the question for me is going to be, I should select the no edges, let's say this edge, and then this edge or something like that, or the minimum number of edges that I should be selecting such that I visit all the points, and the cost associated with this selection is the minimum. Okay. So that's
Sujit,
how
can I ask a question here?
Yeah.
So Fij then is the distance between points I and j, or what is it?
So Fij is okay. So here distance and the fuel consumed by the vehicle is the same.
The same, right?
Yeah. So we are going to use the same. So and hence it is going to be distance or a fuel, both.
And are we assuming that the UAV could actually come back to the same refueling position? Or is that also not? Yeah, it can, right?
No, yeah, it can come back to the same refueling.
But it would not want to go to the same points, because that will just add further distance, right? Okay.
Yeah. Okay. So let's say that if I take this particular point and then I just add this every time I just go everywhere. So I'm just adding all these weights, unnecessarily increasing this entire cost, while my objective is to minimize this cost. And by going to that, and then second thing is that you want to go. So the constraint here is that you want to visit it only once.
Yes, for where you're taking the image. So the UAV must go only once to the image locations, but actually for refueling, it can come back.
Yeah, for refueling, it can come back. Yes, for refueling, it can come back to the same site. Yeah.
Okay, great.
So although it is going to take, let's say that you take this particular node, right? So while going like this, it can come through this. Okay.
Right.
And the second time it may go like this and it can come through this, but it won't take the pictures around this. Okay. So the second time it will be, because the route is coming through that node, but it is not taking the picture in that node.
But all nodes are connected to all other nodes, right?
Yeah, it's an all fully connected network.
So it wouldn't really visit through those nodes necessarily.
Yeah. So it is just that, I think, let me see this, if we can change the pen color. Can we change the pen color? No, any idea?
It's a good question. I haven't tried to.
Okay.
Yeah. Okay.
So basically, like you. Okay. So here, what happens is, you have a direct node from here to the location, right? So it is using that particular edge, but that particular edge could be just passing through other nodes.
Right. Okay. Fair enough. Yeah. Thanks.
So what you are telling is that what we are using is that it's a degree constraint, which basically tells that I think it's you might have already know this. So basically, like the in degree and the out degree of the node should be the same. Okay. So the number of edges going in, the number of edges going out. Okay. And each target should be visited only once. So this is a constraint that we are putting. And the other thing is that, so now what you're doing, you're trying to find tours, right? So while finding tours, what can happen is that, so the finding tours is basically you're just accumulating different tours. So you can end up having tours that are disconnected. Okay, so which basically means that your graph is being partitioned out. So you don't want to do that, because you will end up having two tours that are not connected, which basically means that the UGV doesn't know how to go from one tour to the other tour. It should be always connected. Okay, so this is more like an exponential, because you need to find all sorts of combinations that are there in the graph to find the tours, and then need to ensure that these tours are connected. Okay, so this is a subtour elimination constraint that we need to consider. The other is the fuel constraints, because UAV has a fuel. So just like how, let's say that we take a car, and then let's say you're in maybe Gurgaon. So you want to go to Delhi, and then you want to go to Noida. So before going to Noida, when you are in Delhi, you want to check if your car has sufficient fuel to go to Noida or not, right? So that's where you're just going to add to the future and then check if there is sufficient fuel that I can go. Then only I'm going to consider it. Otherwise, I'll not consider it. So this is an ensure fuel conservation when the UAV travels between two targets. Okay, similarly, when you also need to consider it when it coming back to the refueling station, right? So you should also ensure that there is sufficient fuel left to coming back to the refueling station. And in order to do some kind of an bounds on how should be your UB, that is the maximum fuel that it takes, right? And the number of tours that it takes, you just basically like make a big some huge upper bound. Okay, and then the total fuel consumed, this is just only for the formulation side, that you need to just make sure that total fuel consumed by the UAV must be equal to U times the total number of refueling visits. Okay, so here the M is basically some large constant that we take, so that it is more than this plus the maximum Fij. Okay, some huge number, so that you have your refueling fuel conservation constraints being satisfied. Otherwise, things can get violated, and you'll end up not getting good solutions. Similarly, you have something on the refueling sites, because you don't want the sites to be too far away. You need to bring them back. So you set the value of this variable ts to appropriate value to use whether you want to take the UAV route decisions into account or not. And then these are simple constraints on the degree. Again, you have some degree constraints on the ground vehicle. Okay, and then limits on your variables, you have xij to be only binary variables. Uij is a continuous variable for the UAV because it's a continuous fuel. And then yts, which is again a binary variable for the road network, which is for the UGV. So then once you do this, then you use, okay, so typically you can use the Cplex solver from the IBM to solve this kind of an MILP problems, which is pretty easy to code both in Python as well as in C++. And it also has nice interfaces with MATLAB. Okay. So then we basically like do a simple simulation on two different road networks. This is a square road network, and you have a plus road network. So the idea of using square and plus is that, and this square gives you an uniform distribution of all those refueling sites for the ground vehicle. While here it gives you a large number disparity, which basically says that now the distance between two nodes are going to be pretty high. We have a different maximum distances between the vehicle, between the refueling sites. So in this case, like how does the routes change was our main question that we wanted to answer. So here you can see that the number of fueling 1, 2, 3, 4. Here also here you have only fewer refueling sites, and they're able to cover. So then what we do is basically like, okay, so now we have simulation results. So you want to demonstrate the applicability of the design routes with the UGV through experiments. Okay. So we have one UAV and one UGV. This is an experiment that we did in the IIIT campus when I was there. Okay, so the ground vehicle is this. This is a simple RC vehicle which has been put with an autopilot, so it becomes an autonomous vehicle. Then we have the 3DR iris. So these are the refueling sites Okay, so you have 1, 2, 3, 4. These are the 4 refueling sites that are available for the UGV. You have the green dots or the green flags marks, which are basically the picturing points or the data points on the area for which you need the coverage. Okay, and the yellow lines are basically like the routes that have been taken by the given by the solver. So this is how the UAV will take. So for example here, right, this route, the UAV will start here, it goes up to here, okay, and then it goes here, comes here, and then goes here. Okay, this is the kind of route that it is going to take. So the arrow marks basically like tell you the way in which the routes are being done. Okay. How do I remove this? Any idea? Okay, it is here. Okay, so this is the first route that it is going to take. It will start from here, it goes up to this data point, and then comes to this data point, and then lands here. So the top, you will see the UAV flight. On the right is the flight profile that of the UAV, that how it is moving along the given the trajectory. On the right bottom corner is the UGV, it and its motion, you can see, and the path taken is on the left side of it. So the entire thing is at a 4x. Okay. So when the UGV goes to its desired location, refueling station, it waits there. So, okay, so this is only a concept. So which basically I don't have a UGV on which the UAV can actually land. So, but the goal is that, it comes and then lands onto the next to the UGV, which basically is depicting the concept that the UAV comes and lands and then it goes, gets a refuel and then it goes next again. Okay.
So, Sujit, the assumption here is that all of the road network is not obstructed, right, in some way.
Yeah, road network is not, there are no obstacles on the road network.
Right. Because otherwise, I mean, it would be more difficult because it could be an unknown terrain too, right? So a large kind of park like this, how would you?
Yeah, so if it is an unknown terrain, then you need to have an active communication between the UGV and the UAV, saying that, okay, we have decided that we need to meet there, but I'm unable to go. So either way, let's change the route, or we need to do some online optimization. Here, the planning is an offline planning. Yeah. So
and are there solutions then for that online planning too that are viable or not at this point?
Yes. So after this, I'll just come to that.
Okay. Cool. Very nice.
Okay. So this is how, so basically like, and then it basically like just keeps doing and then going around and come back. Okay. Anyhow, so one thing was that, let's say, so the number of nodes that are there, right? So it was only, we could go up to maximum of 20 nodes or something like that. So 25 nodes would take you like 2 or 3 days to solve the problem. And then 30 nodes was like, we could not solve the problem at all. It's simply because it's computationally quite intensive, and the complexity just keeps growing as you add the number of nodes. But in reality, you can't have such a situation, right? So you want to go to a location and then you just can't sit a couple of days just to make your solver run the problem and then come back. And by the time it comes back, some situation changes and then you may have to redo everything. So for that purpose, we came up with a heuristic strategy that tries to give a decent solutions, not the optimal one, but at the same time it tries to minimizes the time to compute tours. Let's say it gives you within a couple of minutes or something like that. So we want to find a minimal set of refueling points such that every data point is reachable. Okay, and compute a tour of the refueling points. So what we do is we'll make it as an first we'll try to find how many refueling points are required to complete the entire area. So for these refueling points, we will consider it as an as a a single depot vehicle routing problem, or SDVRP, and then try to solve it. To find the computing minimum points, we use hitting set methods. Basically, like what it does is it makes a disk of radius, this UAV distance by 2 around each data point, right? And then you take each point on the UGV, on the refueling stations on the UGV, and then see how many disks it hits. And then you try to maximize the number of disks that is being hit by a single point, and then try to use those, because using that particular disk, you will be able to visit the maximum number of nodes. Okay, so it has a greedy, but at the same time, it gives you sufficient information about how many refueling stations that you really needed. Okay, so and then for each refilling station, you just basically make a SDS, single depot reloading, which is very fast to solve. So you don't need much of computation, which basically means that you can do it in online, especially the kind of problem that you just asked, right? So when you want to do it very quickly, then this is the way to do. Although it doesn't give you the complete optimal problem solution, but it does pretty good job. Okay. So we will move from there to the next different kind of problem, but still we are moving on the monitoring side only. So is there any questions that you have on SDVRP or anything else? Then otherwise, then I can move.
None from my end. Yeah.
Okay.
Please carry
on. Okay. Okay. Yeah, Ramandeep.
Yeah. Hello, sir. Great topic. I have just one question. Which software did you use for deciding the waypoints and autonomous ground vehicle system?
Oh, mission planner.
As a mission planner, it's same mission planner like we widely use for these autonomous system.
Yeah, same mission planner.
Okay. I have a couple of more questions, and that I can ask at the end.
Okay, sure.
Thank you.
So we'll just go from there, and then we'll see that. Okay, so now I want to do path monitoring on a terrain. So basically, like let's say the border patrol, or any kind of an linear path patrolling that you need to do along the mountainous region or things like that. So how do you monitor it when you have, let's say, couple of UAVs that are available to you? And the UAVs always anyhow have the refilling station, most of the constraints that we just considered. Okay, so we'll model this as an 1.5D terrain. Okay, so monitor linearly approximal features. Okay, and then visibility constraints due to terrain. So because it's a mountainous terrain, so if you have a camera which is on top of one part, you will not be able to see the other side. Okay, so now the question is that how should I distribute the paths between these UAVs so that the entire terrain is being continuously covered? Okay, so visibility constraints due to the terrain, and then we are interested in persistent mission planning with heterogeneous robots. So heterogeneous robots in this sense that we have both UGVs that will go along this road, and then UAVs may be there which will be flying on the top. So you are going to consider a team of these two agents, and then you give paths to the UAV and the UGV, and then they will just monitor their assigned paths only. So we can consider this as a 1.5D terrain. Okay, 1.5D is it's a linear feature, so it's like an 1. And then because it's a UAV that is only flying at a fixed altitude, so it is a 1.5D. Okay. So the terrain, you'll consider it like this. Okay, so the UAV is only flying is this blue line. Okay, it is not flying anywhere else. So if I take a point over here, so because of the UAV, so the visibility is constraint is just fixed to this particular box only. So anywhere I'm in this particular triangle, right, the UAV can see the point. So these are the visibility constraints that we drive. So terrain visibility. So we'll define some points. One is called chain visibility. This is called the chain with the curve on which the UAV flies. That's called a chain visible curve. Okay. The regions that are formed due to this visibility constraints, they are always in convex. Okay. And then we will call the visibility points as let's say if I take an endpoint over here, the visibility point, okay? So all the region that is visible on the terrain is called visible segments, okay? And when I project this onto the chain visible curve, okay, and then I'll get this stuff which is called as visibility region. Okay, so this visibility region has 2 points, one towards my left and one towards my right. So I call them as left viewpoints and the right viewpoints. So the left viewpoints are in magenta color, the right viewpoints are in green color. I hope the model is very clear now. So now we want to do a persistent monitoring. Well, let's say that we take a UAV and the UGV. So there are two refueling, possible refueling sites for the UAV here and here. So it's like this. So just like in the previous case in the UGV, on the road, we gave them a set of refueling points, right? And then of that, it picked few. So similarly here, we give them a set of refueling stations, and the UAV needs to pick whichever it is going to use. And whenever it tries to pick one, it will always incur some cost. Because of that, you don't want to just keep moving between refilling stations. Rather, once you open a site, you just try to use only typically that site, unless and until you need another site because of the coverage and the refilling constraints. Okay. So we will use the UAV and the UGV to do a little bit of an persistent monitoring, and then you have constraints on the aerial robot refueling, and then we'll try to find a tour kernel, which basically means that you're going to find subtours for each of the vehicles. Okay. So the problem statement: given a 1.5D terrain and a set of ground and aerial robots with optical sensors and fuel limitations of the aerial robot, plan routes for the robot, okay, such that all points in the terrain are observed by at least one robot, and the maximum path cost for a single robot is minimized over all robots. So why do you need the second one is basically, so why do you need basically this constraint that we are interested in? So this is mainly because I can have two robots, and then I can make one robot cover 99% of the work, and then other guys will do only 1% of the work. Okay, so that is not pretty good with respect to using the fuel as well as the machine. So you're majorly dependent on only one vehicle to do most. So you want to minimize that, misbalance. So you want to do the maximum path cost for a single robot is minimized, which basically means that uh, if you take an error between these two paths, then that should be less. Okay, so the maximum path cost for a single vehicle is minimized. So that is what it is. So again, I'll not get into the MLP, which is a pretty longer than the previous one. So again, we will do a mixed integer linear programming problem. Okay, and then we'll try to find the solutions. So I will show through two examples. We'll use 6 robots, 2 ground robots, and 4 aerial vehicles. So UAV1 and UAV2 are operated at 1500 and 1800. So depot opening cost is set at 1000 units, and each instance was offered a maximum of 36 seconds, which is for the entire computation time. Okay. So this is the kind of the same setup, but 2 environments that we look. So consider this environment, which is on the left. So A1 is the vehicle UAV, 2 UAVs, if I'm not wrong, that are traveling on. So UAV1 and UAV2 paths are on A1, UAV3 and UAV4 are on A2. Okay. So if I take this particular thing, so because they're operating, so you have one refueling station that this is the start location of the UAV. So you have one refueling station that has been opened up here. Okay. And this is a second refueling station that has been opened up. Okay. So what is the path? The path for the UAV2 is going like this and then going there. It goes, comes back. That's it. This is a path for the UAV2. Okay. So, and then you have a UAV1. UAV1 path is very simple. It goes to the top and comes back. Nothing else. See, by going to this particular location, what it does, it can see all the points around this. So it's typically just covering this complete area. Okay. So what happens? And then this guy, what is he doing? Going up to here, he's completing this complete area, right? From here, he can see everything. Right. So this entire area is being covered by this particular UAV. And because he's at this location, he can also see the stuff around this. Okay. So we are left with only this part. So here there are two UGVs, UGV1 and then UGV2. UGV1 is starting at this particular location and UGV2 is starting at this location. So what is the optimal path taken here is the UGV1 will move from here to here, okay, and it can sit at this location. And then UGV2 will basically like move from this location to here and then it sits at this location. Okay, by doing that, you are able to get the complete coverage of the entire terrain. Okay, similarly, for the second vehicle, you have your start location. I think start location is here. It goes here, goes there, up to here. This is the refilling site that has been opened for this, and then this is the path that it takes, and then you have only one UGV that is being used. So here in this, depending on the terrain, you'll have the number of vehicles being operated, the altitudes that they pick is different. All these are part of the costs that comes out on the solver, depending on how your terrains are and how your operating costs are. Okay. So again, once we do the simulation results, we try to do an experimental evaluation of this. So this was done by my collaborator Pratap at when he was at Virginia Tech. Okay. Okay, sorry. So this is the terrain that we are looking. So the UAV is flying high. So just basically like it starts from here and it goes up. And the UGV is doing an 1, 2, 3. Again, it comes back to 4 and 5. So this part it just is doing. So if I'm not wrong, I think here you can see the UGV. UGV is doing its part and then the UAV is doing its part. So UAV has went, done, come back, and then again it flies and it goes to some other location at 4. It lands there and then again it comes back. Okay. So this is very almost similar to the one that we just did in the for the previous experiment. Okay. Okay. So from 1.5D, the next we did the extension to 2.5D. So now you have a proper, the hilly regions and things like that. And but still we 2.5D because we don't do in complete 3D, we still make that UAV is flying at a constant altitude. Okay, but here a small variation is that we are interested in monitoring only certain points. Let's say these are the points that are of interest. Okay, this, and this, and this. But these are the bottom points are on the terrain. Okay, these are the points that are interested. So when they're on the flat plane, so all these are at the same altitude h. Okay, so we are interested in area coverage in realistic environments. Okay, terrain features, buildings and altitude variation limit visibility, and then randomly placed targets. Okay, so this is the whole idea of the thing. So the entire altitude is h. So you want to take pictures at these locations. So one way is that you go to each of these locations and then you take the picture, but you're not utilizing the field of view of the camera that is available to you. Okay, so we want to use the field of view of the camera and then find the minimum route that is required for the UAV to take the pictures. So here, if I take a point Pi, then, so I can see all the points around the global horizon from here to here, everywhere, right? Anything less I can't see from here, so I need to go to a different point. So what I do from this, I project it up. So when I project it an interface with respect to different terrains, right, I'll get various crazy polygonal structures. Okay, so and then these polygons basically tell that if I'm here or I'm at this location or anywhere else, anywhere along this boundary, then I can just see this point. Okay, so and then I can have multiple viewpoints or multiple of these visibility regions that can overlap with each other. So if they overlap with each other, I can just do one thing. I can just come to this particular location here, right? And then I can take a picture at this point, then I will be able to cover both the points. So similarly here, right? I can come here, then I can just cover both. So I take these regions and then I discretize them, and then I try to solve it as a generalized traveling salesman problem with neighborhoods. So typically in your TSP, which is a traveling salesman problem, right? So you have a set of points. You want to find the route that minimizes the travel time by visiting all the nodes, right? So here what you have is, instead of node, I have a small region around the node. So if this is the node and then I have a small region around the node, it is okay for me to just visit any point along the neighborhood that is good enough as visiting that particular node. So if I'm giving a set of neighborhoods, let's say, then I can just come and visit just only 1 point or 2 points or something like that, and then still I'll be able to visit the nodes. So discretize because it requires nodes, and if it's a continuous, then you can have infinite number of nodes. So for that purpose, we use some delta, and then you discretize the points and then convert that to a GTSP problem, and then we try to solve it. So once we solve, then you will get a path. So for this, what we did was basically like in Triple ITT campus, we first flew the UAV. We got the 3D point cloud of the UAV. 3D point cloud of the area that we are interested in, and then we placed some markers here. Okay, I don't know why. Here you have 2 red markers, and then here you have 2 checker markers that we placed. And then because of the presence of the buildings, that will give you this conic structures that you're interested in. And we just used a simple P4 to get the paths. And then from there, we got the visibility regions of different points of interest that we want to monitor. Okay. And then when we solve it, so you can see that for checking all these 4, there's only small path that is required going from here to here. That's it. Yeah. So basically, like by visiting a small set of points or making your paths smaller, you're using the field of view of the camera to get your things done. Okay, is it good?
So a question here, Sujit, that the visibility depends on the height also, right, of the UAV.
Yes.
So I mean, what are you suggesting, that we are fixing the height first based on maybe what resolution we want of the photographs that are taken, and then
yes,
use that as an input?
Okay. Yes. You fix the field of view. So you fix the altitude at which you want to fly.
Right.
So I can have a very long altitude, and then I can see almost everything, right? Then I'll become
right.
So, but then as I
like
limit my altitude, I can only see so much.
Right.
And then because of the terrain constraints, that will also add a bit, because now because the visibility is less, right? So then the number of points at the places that I need to visit keeps increasing.
Right.
H is an input to the input to the parameter. Yes, you're right.
Right. Okay. Great. Thank you.
Okay. Okay. So how am I doing on the time? Is it fine?
Yeah, we're fine.
So one thing is the last one is basically now we found all the tours. One thing that we missed was basically on the landing part. So for landing, typically the GPS based landing will always result in an error because GPS has some error. So depending on 1 to 3 meters as of now, but I think with the RTK it is less than a meter that you can get, right? But because of the wind disturbances and all, that will create some more issues. So we want to land precision, basically like accurately on a given target location. For that purpose, we use a vision-based landing system. So for this, we developed an guidance for the UAV based on the perception of the target on how the UAV should keep moving such that it basically lands on the target accurately. Okay, so for that, so one of the things is that you start having a velocity at which you are coming to the target, to the landing pad where you want to land, but at the time of landing you try to slow down, right? So basically like what you're trying to do is you're trying to match the velocity of your vehicle as well as with the target, and then you try to land slowly. So that means that the closing velocity tends to zero as you move towards the target location, right? So for that purpose, we developed a simple closing velocity controller based on a log polynomial framework. Okay, so and then we are going to use a pure pursuit guidance law, which is basically says that if you're seeing a target in front of you, you try to align your heading direction towards that. So if you align towards the target, then hopefully as you time progresses, you will be going and meeting with the target. Okay, so here we have a polynomial function that basically that we will use. So x is a function of my initial distance between the current location of the UAV and the target point where I want to go and land. Okay, r of x is the current distance. Okay, so based on this ratio and then taking a log, I'm going to change the velocity at which I'm going to give to the vehicle. So my v of u is okay. Sorry, my v of u is velocity of the target and f of x. Wherein if it is stationary target, we assume that there is a small random v that is v of t is available. Otherwise, it becomes infeasible. Right? So by changing the polynomial values of a and b, you can get different characteristics. So here you have a fully decelerating values of the closing velocity controller. So here you have increasing, first you accelerate and then you try to decelerate. So you can, depending on the situation and then the kind of features that you like, you can change the a and b such that it meets to your requirements. So this is the I think overall framework that we use. So here you have an USB override camera, and we used an iris, and then later on we shifted to solo. Yeah, and then we used a ball, basically like a red colored pad. And then I'll show you later. Like we had to go more than just only the pad because of all the visibility constraints due to the coloring when the vehicle comes closer and closer towards the landing. So as the vehicle comes, when I have a big landing pad, the entire camera is just full of the same color. So when it is at the full of the same color, it is not able to differentiate where it should land. So when it tries to say that, okay, I want to initiate landing, then by the time the target will move because the target isn't moving, right? So for that purposes, what we did is that we used this RQ markers. So so you have a switching condition when you are, let's say, around half a meter from the target, okay, and you're trying to land. Then the vision system switches from the red color detection to RQ marker detection. Based on RQ marker detection, it becomes more clear and close that you're almost okay. So you're almost closer to the target to land. Okay. Okay, sorry. I think these are. Okay. So, and in order to know, like, what was the trajectory of the UAV, so here you have a small GPS with the Pixark, so that you can record the trajectory of the target. So we also tested with an occluded target. Basically, like you switch off or you close the target for some time. So, and then you can see that the estimator is trying to find where it is, and then it uses the estimated values. And then once it is back to visible, again, it will try to track it. Okay. Yeah. So that's it. So basically, like in conclusion, we developed algorithms for UAV, UGV coverage, for monitoring. We have the heuristics as well as the optimal planning. And although as of now the problem setting is more deterministic, so stochastic versions is where the future directions is. So there is an uncertainty in planning. That's exactly the point that you had asked. And then extension to multiple vehicles in coverage and some kind of a more dynamic scenarios. Yeah, thank you.
Very cool. Thank you, Sujit, for a very interesting talk. I mean, I guess, what would you say are the big challenges going forward with UAV and planning? Is it really navigating spaces with bigger obstacles that in real time? Is that kind of an area of work that you're pursuing, or what are the other areas that you think are open challenges?
So as of now, it's basically the uncertainty in the environment that you want to look at. So there is a lot of work that is left in there. Let's say even with the wind disturbances, things like that, because it changes every day, right? So
Right.
how do you learn that you'll be able to do it with different? One is there is a lot of scope on using reinforcement learning and trying to come up with different guidance policies. The new ones is basically like, how do you use, let's say my research work is more as of now on the swarm side, wherein I use a team of swarms.
Right.
Okay. So there are two aspects. Assuming that I am the operator, right? And I want to drive the swarm from one location to another location. Okay. But at the end of the day, I am the human operator, and I need a control. I want the swarm to be autonomous, but at the same time, it should be responsive to what I want it to do. Right. So, but I can't handle too many people. Let's say I have a swarm of 100 UAVs. Right. So then how many UAVs can I handle? Is where I'm looking at. Like, say I can handle like one or two. So if I am able to handle only one or two, then where should they be placed, so that just I manage only these two, and then the behavior of the entire swarm system emerges by designing the control laws or designing the behavior laws, so that you can drive this complete swarm from one location to another location. Okay. So I'm looking here, and we are basically like, we are just setting up the swarm lab here, and then we have some VR systems that we're developing. So then interface the VR and the swarms, so that you can drive the entire swarm from one location to another location. So why VR rather than using any kind of a control on the keyboards is basically like VR gives you much more handle right? It gives you the realistic, like how things are moving, and you will be part of the entire system rather than just as an operator.
Right.
So other
Okay.
thing is, let's say that there is a swarm UAVs that are attacking you, right? So in that case, I want to basically like find ways in which I can disable few agents inside the swarm such that the entire swarm breaks.
Very interesting. Okay,
So
so
it's a reverse question of what previously I tried to do. I
right.
want to find fewer agents so that I can control the entire swarm. So I want to find like fewer agents who are basically disabling them will basically like disable the swarms. Or
Right.
alternative is that, let's say, most of them have some kind of an obstacle avoidance, right?
Huh.
So whenever the agents are so when you have a swarm and the obstacle comes, the swarm is either entirely shifting or they will break up and then rejoin. Okay, that's
Right.
the kind of property that you want, right?
Right.
But
Right.
now I can intelligently send these obstacles so
Huh.
that they will never come back. They will never be
Okay.
able to join. So which
Very
basically means
interesting.
that they'll end up splitting up.
Right.
So
Interesting.
these are the inverse problems that I'm trying to look, because eventually I think the swarms will come. It's just a
Yeah.
matter of time. Yeah.
Right. And these are in security applications primarily, I mean, that you're looking, or what other applications
Yeah,
are there?
it is primarily security
Huh.
applications. That is true.
Okay, very
And the other
interesting.
ones which I'm doing is on underwater vehicles for adaptive
Right.
sampling, stuff like that. Yeah.
Oh, nice. Okay, very nice. Thank you, Sujit. Ramandeep, you had some questions. Would you like to ask them now?
Yes, sir. So just one small question.
Yeah.
Okay.
So this it's about your MILP problem.
Yeah.
It seems like we haven't considered the altitude factor in that one. Are we considering that as a 2D planar issue? Because
No, so altitude is basically like just the operating. You just consider it as a fixed cost. So whenever you want to land, you just use another additional factor, because from the time it goes to that altitude and then comes down, you just add that cost. So takeoff cost and the landing cost are some constant costs that you added.
so that's exactly my question, because the altitude is fixed and our problem is to reduce the cost function.
Yes.
Like I know that just reducing the altitude by 2 feet will drastically reduce the thrust required to keep your drone up.
Yeah.
So varying altitude can actually like comes up in a reduced function cost.
Yeah, you can use that as another. See, the thing is that when you start to play with altitude, right? So your viewpoints change, right? So that's why we had only two fixed altitudes rather than making the entire altitude itself as a variable. We had two different altitudes, and then take altitude 1 or altitude 2. So it'll have each has different operating costs.
Fair enough. Because this mission planner, it can do altitude waypoints as well, right?
Yeah, it can do.
And we can connect this graph resolver with that mission planner so that it can create an automatic waypoints.
Yeah.
Fair enough. Interesting application, sir. I mean, I'm really glad to part of this session. Very, very insightful. Thank you very much, sir.
Thank you.
That's about it.
Thank you, Sujit. So I hope to catch up with you soon and, get more insight what we are doing in the agriculture domain.
Sure.
And how we can collaborate on that.
Yeah. I'm looking forward for that.
Wonderful.
Thanks a lot.
Thank you. Thanks so much.
Thank you.